Okay, hello everybody. Welcome to your new chapter. Hopefully you guys enjoyed your spring break. This is probably my all-time favorite chapter, and I know I say that a lot, but nuclear chemistry is super, super interesting. So just make sure that you are following along with your notes, and let's go ahead and get started. Okay, so to begin, we have numbers 1 through 3. So I'm sure you guys have heard the name Marie Curie. She's very, very famous, but she was one of the people to help discover nuclear radiation. So she's really important along with Becquerel. Becquerel was actually Marie and Pierre Curie's teacher. So they were actually taking classes by him and trying to discover what was going on. So Becquerel was a teacher, and Marie and Pierre Curie were his students. Marie and Pierre were married, so that's kind of adorable. But basically, they discovered it totally by accident. So basically, what happened was in 1986, Becquerel was somehow got his hands on uranium salt. Remember, this is the time before they knew that uranium and radioactivity existed. So he was experimenting with it. So he placed the uranium salts that he had in the sun, and he had a photographic plate on top, so like photo paper. And so what happened was that the salts left a perfect photo of itself onto the paper, the photographic paper. So he thought, hey, there must be some type of interaction between the uranium and the sun, and it is releasing X-rays. At that time, they didn't know what X-rays were. However, he wanted to do it again the next day, but it was cloudy, so he didn't have the sun to be able to do his experiment. So he left the salt, the uranium salts, with the photographic plate on top of it in his desk drawer, and he actually came back the next day and saw the same exact result. So he was like, what the heck? Like, I'm not supposed to be able to see this? I thought it came from the sun's energy. So he discovered that. Marie and Pierre Curie came along and helped him really discover what it was that was going on. And so this is now what we call radioactivity. So basically what radioactivity is, it is the spontaneous emission of rays or particles from certain elements. So for example, uranium, polonium, radium, radon, neptunium, a lot of elements are radioactive. And it's because they emit rays and particles. And this all leads to something called nuclear radiation. So nuclear radiation are the rays that are emitted from that radioactive source. So if you're holding a piece of uranium for whatever reason you want to, the rays being emitted is what we call nuclear radiation. Pretty dangerous stuff. It's not something you really want to mess around with. And later you'll learn about how Marie Curie and a lot of scientists during this time died horrible deaths from playing with radioactive materials. So that's fun. Okay, so this is a big slide. We have numbers 4 all the way through 11. 4 through 11. So radioactivity, right? That is the particles being released. This is an example of something we call radioactive decay. So this can happen with both chemical and nuclear reactions. So as we know, we talked about this in previous chapters, whenever a chemical reaction occurs, it is to help the atom become more stable. So that's really its goal. It wants to become more stable. So the same exact idea is with nuclear radiation as well. Now, what makes it very different is that chemical reactions, like we talked about in, gosh, when was that, last semester, that they will bond with other elements in certain ways to have a stable electron configuration, the octet rule. So that's what chemical reactions will do. And typically they're not, dangerous or anything. But nuclear reactions start with isotopes that are unstable. So these are what we call radioisotopes. So this means they have a very uneven number of protons and neutrons inside of its nucleus. So to make the isotopes more stable, changes occur into their nucleus. So instead of just gaining or sharing or losing electrons, they will change their nucleus. So electrons are on the outside shells. Those are pretty easy to pop off, but trying to change the nucleus is a lot more difficult. And so whenever we see these changes, it emits a large amount of energy, which is part of the reason that nuclear reactions can be so dangerous, because it releases a lot of energy, and often that energy is not something that you want to play with. Now, the crazy thing about nuclear reactions is that they cannot be slowed down, sped up, or stopped. So once you have a nuclear reaction happening, you literally can't control it. Okay, so we'll talk about this more later with nuclear reactors, why you really need to make sure that the scientists know what they're doing, because if something goes wrong, it goes really wrong, and it can't really be stopped. Chemical reactions, you can change the temperature, change the pressure, add a catalyst, and that controls it. But nuclear reactions, it's just gonna do its thing. It doesn't care what anyone thinks, it's just gonna go for it. So definitely important to know what you're doing when you are dealing with these these radioactive elements. Okay, so we've got numbers 12 through 14. So radioactive decay is part of the way that it will cause it will make it more stable. So basically, it doesn't need any input of energy. You don't need to do anything to it. It is spontaneous, so it just does it on its own. So it releases things from its nucleus to become more stable. So if the product of a nuclear reaction is unstable, it will decay as well. So for example, carbon-14, that is inside of all of our bodies, and we use carbon-14 when we're trying to date like tree rings and things like that, and we'll go more into that radioactive dating later. But when carbon-14 decays, it actually decays into nitrogen-14. And nitrogen-14 is stable, so it's got its protons and neutrons nice and balanced inside of the nucleus, and it's nice and stable. So that's just one step, no big deal. But if we look at uranium-238, it goes from uranium-238, it decays into uranium-234, but guess what? That's still not stable. So it's going to decay again to thorium-230, which is still not stable. Then it goes to radium-226, etc., until it finally reaches the stable lead-206. So going from uranium-238 to lead-206, it has to go through 14 steps of decay. 14 steps, that's a lot. So some take a long time. I mean, that process takes billions of years, while carbon-14 has well, we'll get more into that later, but it takes about 5,730 years. So once it is stable, so for example, once we have the carbon-14 has decayed into nitrogen-14, it is no longer radioactive and is stable. So once it's stable, it doesn't feel need to release any energy. So we've got number 15 and 16. So radiation is emitted as it decays, right? And there are 3 types of nuclear radiation. So we've got alpha, beta, and gamma radiation. So those are the main 3 that we're going to talk about in this class. So the first one, alpha, this is 17 through 19. 17 through 19. So alpha radiation is the weakest of the 3. So what it does is it emits a helium nuclei. So what helium nuclei look like? It's 2 protons and 2 neutrons. So as we can see in this image here, we have uranium-238, and it decays into uranium-234, or sorry, thorium-234. And to become thorium-234, it has to emit a helium. So we can see we have 2 protons and 2 neutrons being released here. So that's all it does. And like mentioned, this one is the weakest of the three. It has a very large mass, a very high charge or a big charge. So they don't really travel very far. They're not going to harm you. I mean, literally sitting here, I am being bombarded with alpha particles and it is completely fine. Like, it's not going to cause cancer or anything. So a sheet of paper or even your skin can stop these radiation particles. So they're really not very strong. We are being hit with them constantly. So nothing really to be worried about with alpha particles. Then we move on into beta particles. So this is 20 through 22. So instead of having 2 protons and 2 neutrons being released, this time it is an electron being popped off. And it takes a lot of energy to pop off that electron. So it does have more energy than the alpha radiation does. Still not enough to really cause concern. We are constantly being hit by beta particles as well. So it's just a fast moving electron. So here, like talked about earlier, we have carbon-14. So carbon-14 is in all of our bodies right now. So we are actually literally decaying at this very moment. So that's exciting. And as it decays, it turns into nitrogen-14 because it was able to pop off an electron. So once it pops that off, then it can form into the stable nitrogen-14 there. So beta particles are really not that strong still, nothing to be concerned about. It can be stopped by aluminum foil or thin pieces of wood. Another, like I said earlier, this is all the time. We are constantly being bombarded with beta particles. Still not really much of a concern at all. But things get a little crazy when we talk about gamma. Now these ones are insane, okay? So this is 23 through 26. So 23 through 26. So gamma, this is a high energy photon. So if you guys don't remember what a photon is, that is a particle of light. So the cool thing about elements or elements that give off gamma radiation is that they glow. So whenever you see, like in cartoons, someone's like interacted with radiation, they glow. That's because it's gamma radiation. It literally glows because it literally gives off light, which is really cool. So going back to Becquerel, when he had the uranium salts and it had an image on the photographic plate, those were gamma rays being released. And if you look into the history of those scientists, they all died from radiation poisoning because this is a very, very high energy particle. It can pass through paper, it can pass through wood. Some of it will still pass through lead. It has to be like 6 inches, I heard, to really block most of the gamma rays. But they are very penetrating, very dangerous. They don't have a mass, they have no electrical charge, they're literally just a particle of light, and it can barely be stopped. So this isn't one you want to play around with. So when people talk about radiation, often everyone like freaks out. They're like, oh my gosh, radiation is terrible. No, not really at all. Only gamma radiation. And gamma radiation, we'll talk about this more later, but it can actually be used in treating cancer patients. It can help zap out tumors and things like that. You just have to be really careful not to put too much in your body or else bad things will happen, which brings me to something called the Radium Girls. If you've never heard of the Radium Girls, you gotta look them up. It is insane. So during World War I, a lot of young women suddenly found themselves without husbands because they're all off to war and they needed money. So they worked in clock factories. Now these clock factories actually paid them 3 times more than what the average job a woman would have during that time. So what they did was that they would paint the watch dials with radium paint. Now radium paint is radium itself is very radioactive and it emits gamma radiation. So basically they would have their paintbrush, they would be painting the clocks, the dials on the clock, And it glowed so that people at night, before there was like a lot of, you know, electricity and stuff, could see what time it was at night. This does not mean that the glow-in-the-dark things we have today are made from radium. We have far safer options today, but back during that time, they just used radium paint because it glowed in the dark. So while the radium girls would be painting, they would need to lick the tip of their paintbrushes with the radium paint on it, just to make sure it had a nice fine point so that they could make really precise paints. And they literally would glow at the end of their shift. So these girls would go, they would be glowing at the end of their shift. And so a lot of times the girls, they would be like, hey, I'm going out to this party. So they would like paint their face with it. Some of them even painted their teeth to make just this, you know, beautiful glow. Unfortunately, it literally destroyed their bodies. So if you are feeling brave, feel free to look up Phossy Jaw. So it's P-H-O-S-S-Y, Phossy Jaw. It literally destroyed their jaws. It like got into their jaws and it would just destroy them. So a lot of the girls, their teeth would fall out, and then it would just be all this like pus coming out. And then as it continued, literally chunks of their jaw would get into their mouth and they would just have to wipe it out. It was a very long, painful death, not a way I would want to go. It caused cancer throughout the body, so if you were lucky enough not to get Phossy Jaw, it would settle in your lymph nodes or whatever, and you would get horrible tumors. One lady back in that time had a tumor the size, they say, of 2 footballs in her abdomen, and she shortly died afterwards. And that was because of painting with radium. So definitely not something you want to play around with. And Madame Curie, Madame Marie Curie, she also died from radiation poisoning. And if you look up the stories of radiation poisoning and those early scientists, it is really sad. Another one, because I don't know, this is kind of interesting to me, just the dark history of radioactivity. Another girl, or sorry, her husband was, and I can't remember his name, but he was, you know, studying radioactive sources, and he wanted to take a picture of his wife's hand using x-rays, right? So radioactive source, that was very strong. However, we know the right amounts of x-rays we should put into someone's body, but at that time he didn't know, and so he just like blasted her hand with all of this radiation, and they got a really great x-ray image, but it actually ended up causing cancer in her hand, and yeah, not a good way to go. So be careful with radiation. And so as we can see, here's the last chart here. So we have alpha radiation. So it is low penetrating power. And remember, that's 2 protons and 2 neutrons being released. Beta radiation, it releases an electron, and this has a moderate penetrating power. And then we've got the gamma, which has a high energy. It releases a photon. That's what the symbol is there. And it's very, very high penetration power there. So in your notes, number 27, go ahead and answer that. And seriously, look up the crazy history of radiation, the radium girls, Phossy Jaw, all that stuff. It is fascinating, but also really disturbing. But anyway, have a good day.